This is section 7.2. We're looking at similar triangles. Now we covered all of the theory yesterday on similar triangles. Now we're going to actually use what we've learned to try to solve some problems. Okay? So we're going to do a little bit of review first. We want to determine the scale factor for the similar triangles here. So the way we determine the scale factor is we just want to divide one side length by the other. The only trick here is to make sure you pick the right side length of the similar triangle. That's the only trick. If you pick the wrong side and you divide them, you're not going to get the right scale factor. Okay? So we know here that these triangles are similar. How do we know that? Who can tell me? Well, let's start here. We learned 3 ways to tell if triangles are similar. What were they? Who can remember? It's at the end of yesterday's lesson. Adrian. There's 3 ways we can tell if a triangle is similar or not to another triangle. How do we tell?
Side, side, side.
Yeah.
Side, angle, side. And
Yeah.
triangle, side.
Good. So if 2 angles are the same, then we know the third angle is the same. If all 3 sides are the same, we know it's a similar triangle. And then if 2 sides are the same with an angle in between them. Okay? And when I say the same, I mean the ratio of those sides are the same. Okay? So that's what we're asked to do here. We're just asked to determine the scale factor. So we know here by side, 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 well, we can check. We can go hypotenuse, so 40 over 25. Is that going to be equal to 32 over 20? Is that going to be equal to 24 over 15? Right? That's what we need to check. So we are checking is triangle ABC similar to triangle XYZ. And we actually know, before checking any sides, we know it's similar because this angle and this angle, this angle and this angle are the same. So because of angle, we know that our triangles are similar. If we know that our triangles are similar, we know that they're going to have the same ratio between the sides. Now, the scale factor is just another word for that ratio between the sides. Now, I like to use the bigger triangle as the numerator, so we're going to get a value above 1, so we're not dealing with decimals as much. So let's say the scale factor we determine as k, that's what we use for scale factor, and let's check AB over XY. Now, I like to use AB and XY because they're the hypotenuse for right angle triangles, and they're less easy to confuse between the other 2 sides. Now, if you're not sure, if you're checking 2 triangles, what side, let's say you have a hypotenuse and 2 sides to check, and you're not sure which side aligns with which side, you would just pick, first of all, the hypotenuse, if it's available. You know it's across from the right angle, so you know that's going to be the side to pick. Otherwise, you would just pick the bigger side over the bigger side. So we know 24 goes with 20 because those 2 are bigger than 32. Sorry, 32 goes with 20 because we know those are the 2 bigger of the 2 other sides, right? 15 and 24 go together and 32 and 20 go together. Does that make sense? So one way is to kind of orient the triangle so in the same orientation so you can pick the sides. If that's too hard, you can go by like in the individual triangle, what side is the biggest? Here it's 25, here it's 40. So you know that the ratio we want to check is here 40 over 25. We can divide both of these by 5. We get 8 over 5. So that's our scale factor. Our scale factor, which we represent is by k, is 8 over 5. All right? Next, we want to solve by cross multiplication. So we want to solve for x. Now remember, what we're actually doing when we're cross multiplying, don't just cross multiply and not know what we're doing, but we're multiplying both sides by x, right? So we would get 5x here over 7 equals 3x over x, because we're multiplying by x, the x cross out, and then we're going to multiply both sides by 7, so we would get 7's cross out, we get 5x is equal to 21, x is equal to 21 over 5. Now we did all of that instead of just cross multiplying. If we cross multiply right away, we can say that 5x is equal to 21, right? 5x, 21. You get x is equal to 21 over 5. Okay? I like to show this because that's the reason why cross multiplication works. Sometimes students just don't know when or why they're cross multiplying, but that's the reason. It's to save those steps. Okay, 21 over 5. Next we have 35 over 3 equals a over 11. We're going to cross multiply. So we're going to get 3a is equal to 35 times 11. 3a is equal to, I think that's 385. So a is equal to 385 divided by 3. We can tell if this goes evenly into 3. Remember that little trick I told you? You add these up. 3 plus 8 is 11, plus 5 is 16. Does not go in evenly, unfortunately. You can do that on your calculator. You'll get 128.33. That's the value of A. All right. Given that triangle ABC is similar to DEF, they told us this already, they're similar, determine the values of B and F. Usually we represent, if it's an unknown side across from a vertices, we call it the same letter, but in lowercase. So if we have vertice capital B, across from it will be side length lowercase b. Likewise here, vertices capital F, across from it, side length f, just to make things easier. Okay, so one way we can determine the values of B and F is we need to use corresponding ratios, right? We know they're similar, so we know that the ratios of the sides are the same. So the first thing we'd want to do is to find the ratio between two sides that we know, right? Or we can call this the scale factor, right? But let's do the ratio. So we're going to do, let's do EF over BC. Okay, and the reason I'm choosing those is because they're both known. I get 35 over 14. Okay, and that ratio is going to be equal to the ratio of one of our unknowns. Okay, so let's solve for, we did 35 on the numerator, so we're going to do 50 on the denominator over B. Okay, any questions here how I developed this formula? Right, I know they're similar, so I'm doing the ratio of this side length over this is equal to the ratio of 50 over B. So now I can cross multiply here. I'm going to get 35B is equal to 14 times 50, which I think is 700. Right? B is going to be equal to 700 divided by 35, which I think goes in evenly.
20.
Is it 20? Okay, B is equal to 20. Now to get the ratio, sorry, to get the value F, we can do the same thing. Okay, we can do a ratio that we know. So same thing, we can say 35 over 14, same thing, is equal to F over 6. Okay, that's my ratio, the same thing. So I'm going to do cross multiply, so we get 14F is equal to 35 times 6. F is equal to 35 times 6 divided by 14. You can do that in one step on your calculator. 15. I'm going to go back and look at the triangles now. Does that make sense? F is 15. Does that seem about right? Half of this 35, yeah, that seems right. B is 20. So 20 here is much longer than 14. That seems right. Any questions? Okay, pretty easy stuff, I hope. Coming from quadratics, this stuff should look really easy. So when solving problems that involve similar triangles, first thing is to show that the triangles are similar with the three methods we talked about yesterday. Side, 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 angle, or angle, angle. You'll set up the proportion of the sides or the equality of the angles. and then we'll solve for the unknown. That's it. All right, let's see. Determine the value of m and n. So the first thing we want to check, are these triangles similar? Now if they are similar, then we can use our ratio of sides to determine m and n. M and n are side lengths. First thing we want to do is determine that they're similar. Who has any idea whether these two triangles are similar? We did review some angle theorem. Pretty easy stuff here. Who can tell me? KG, yeah? I could do that, but I want to find out if the triangles are similar first. And I wouldn't use side, 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 because m and n are unknown sides. We need all the side lengths to do side, side, side. Lucas? Yeah, we could use AA right off the bat, because we see this angle. We know that these two angles are what? They're the same, right? So we'll mark them by X. We know they're the same by the angle theorem, right? So now we have angle, angle that are the same. We can say that this angle is the same as this angle. Okay? So we know that the similars are triangles, or sorry, the triangles are similar. So triangle ABC is going to be similar to triangle CD. This is cut off here. What's this letter? Can anyone see it? Nobody can see it, right? E? Yeah, we'll call it E. So it's similar to triangle EDC. Okay, it's important that you get these order right. That A corresponds with E, D with B, and C with C, right? And we know that because of the angles. Okay, we know that they're because of angle, angle. Okay, so we have the triangles that are similar. Determine the value of m and n. So now we can get our scale factor. So we can say 6 over 4, this side over this side, is going to be equal to 3, this side, over n. Now the only way you mess this up is if you put the wrong side, you correlate the wrong side of the triangle. You guys understand that? You have to pick the side that goes with the side. Now the way you can do this is you can either reorientate the triangles or use the angles. I know that 6 here, CE, is the same as 4 here because I'm going from the angle X to the angle circle. X to circle, X to circle, that side length is this side length on the other similar triangle. Any questions? All right, now I cross multiply to solve for n. I get n is equal to 2. Now I can do the same ratio, 6 over 4, and I can make that equal to my other unknown m is going to be over 5. I know m goes with 5 because they're both opposite angle x. Cross multiply, I get 30 equals 4m. M is equal to 30 divided by 4. M is equal to 7.5. Okay? Any questions? Yep.
The 6 wasn't there. That would be like a lowercase d or something.
This, it would be lowercase d, yeah. Cross from d, yeah. Yeah. I don't know why they actually used m and n. They should have used c here, and they should have used e here. Yeah, good point. If you have a hard time seeing what is happening in overlapping triangles, redraw the triangles as two separate figures. So that is a hint for this question. If you can't see what's going on here, because there's two triangles in one, you can redraw these out to look like this. Okay? But this happens all the time in word problems. That it's like a triangle within a triangle. Okay, there's still similar triangles. We know because of angle, 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 right? T is the same angle. And S and Q are 90-degree angles. So right off the bat, we can say that triangle QPT is similar to triangle SRT because of angle, angle, angle. What is the length of QT? So we need to find this length here. We have 4 for the smaller triangle, but we don't have QS. So we're going to determine the ratio of the sides by taking 2 sides that we know. Okay, so we'll do 9 over 3. That's this one over this one is equal to QT, because we started with the bigger triangle on the numerator. So QT over 4 ST. Okay, cross multiply. We're going to get Q3QT is equal to 9 times 4, 36. QT is equal to 36 divided by 3 is, what's that, 12? QT is equal to 12. Okay, next one, we're going to say if PT is 15, what is the length of RT? So PT, they're telling us here, this length here is 15. Now we can use the same ratio that we did for the first one, which was 9 over 3, because again we're dealing with similar triangles, is equal to the bigger one, so 15 over RT. Cross multiply, we get 9 RT. Three times 15 is 45. RT is equal to 5. Okay, you can go back and check, does that seem right? RT is 5, this is 4. Yeah, that looks right. RT is 5. QT is 12. This is 4. Sorry, this is 9. That looks about like 12. That's good. What is the length of PR? So PR is here. So this one is a little different. It's not a side length of a triangle. Anybody have any idea how we can figure out PR? PR. Yeah.
15 minus 5.
Yeah. You're going to do this whole side minus this. So it would be PT minus RT. This side minus this side is going to be this. So PT we calculated to be 15. It was given to us. Minus RT is 5. So we have 10. PR is 10. Alright, super easy so far, I hope. Example 6. A triangle with side lengths 5, 11, and 15 is smaller to another triangle with the longest side length of 24. What is the perimeter of the second triangle? Okay, so we're going to draw the first one. Now we don't know it's a right triangle, so we can't say that this is 90 degrees. We can say that this is, actually, it would look a little more like this. This is 5, this is 11, and this is 15. Okay? Is similar to another triangle with the longest side of 24. So we're going to say, here's our other triangle. It's longer. It's similar, so I'm going to mark my angles as the same. And it says the longest side is 24. Alright? Any questions how I came up with those two triangles? Arguably in a word problem, the setup is the hardest part. Very difficult to teach, but that was my thought process. I'm drawing a triangle, I'm labeling the sides, I'm drawing another triangle, similar but bigger. What is the perimeter of the second triangle? So we know they're similar, but we in order to get the perimeter, what do we need to find out? Jaden, what do you think? to get perimeter of a triangle? You know this. I'm not trying to trick you. Perimeter of a triangle. Sorry? I think if you were paying attention, you would have had it right away. Rudy, perimeter of a triangle. How do you find a perimeter of a triangle? Any triangle. Yeah, just add up all the sides, right? So we want to find the perimeter of this triangle, the larger one. We need to find all the sides. That's what we have to do, to add them up. We have 24. Now, there's a good reason why they gave us one of the sides and told us that it was similar. So we can find the ratio between the sides. So what we can do is we can say 24 over 15, that's our ratio, because that's our longest side, is going to be equal to, now I can pick a side here. Let's call this A and let's call this B. I'm going to say A, because we're going to solve for this one first, over 5. Because that's the side that corresponds, right? And now we can solve for A. 15A is equal to 25 times 4, I think is 120. A is equal to 120 divided by 15. 8. Yeah.
Wait, so you did tell me. Oh.
A is 8. Again, we can do the same thing for the B. We'll do the same ratio, 24 over 15 is equal to, now we're going to say B over the B side, which is, I don't know why I put 4 here. This was supposed to be 11. 5, 11, and 15. No idea why I put 4. It's B over 11. Cross multiply, we get 15B is equal to 11 times 24. What's that? 264? 264, and then divided by 15? 17.6. 17.6. That's it. 120? I divided, 120 was 24 times 5. Because we cross multiplied. This is really easy stuff, guys, compared to the last chapter. The only way you don't do well in this test, you don't study and you don't do your homework. Lucas.
When you're naming triangles, does it matter what way?
With the letters, A and B here,
Or like for like question or example 5, like you did Q, when you go like
QT or TQ.
you go the other way.
Yeah. The only thing I would say, if you go the other way, like if you call it TQ, you go the other way with the other triangle as well, right? That's the only thing you want to do. Technically, you could even do that the opposite, and you get the same answer because it's the same length, right? Yeah, but it's always important to try to line up the vertices.
So we're gonna do a quiz then test.
Yeah. Okay. Next page. We're gonna get through this one. I think we can do another lesson. Ratio of perimeters, altitudes, medians, diagonals, and angle bisectors. All right. If two polygons are similar, their corresponding sides, altitudes, medians, diagonals, angle bisectors, and perimeters are all in the same ratio. So example, if the sides of two similar triangles are in the ratio 4 to 9, what is the ratio of their perimeters? Given the following diagram, determine the width of the river. All right, so I don't know if you can see this diagram. I think you can see it better than I can here. Let's zoom in a little bit more. Okay, we have 20 feet here, 32 feet, 75 feet, and we have W feet, unknown. Okay, so the first thing we want to do, we know we're working with triangles. We want to see if these two triangles are similar. How can we tell if they're similar or not? RC, what do you think? Are they similar? This triangle, is it similar to this triangle? Why? Say it again. Yeah, that's it. The angles are the same, right? We know this is 90, this is 90. We know these two are the same, this angle and this angle. Because of our angle theorem, opposite angles are the same here on two straight lines, right? So then we know that by angle, we can say triangle, and I'll label these A, B, D, and let's do A, B, C, and E, F. Okay, I can say triangle A, B, C is similar to triangle. Now I need to get these right. This is X angle, so we went A, B, so X to 90. So this would be F, E, and C. These two triangles are similar by angle. Okay, so therefore our ratios are the same. So if we want to solve for W, we can first do our ratios. So let's do this ratio here, 75. I'd like to start with the larger one always, 75 over 32, just so I work with whole numbers here or larger than 1. 75 over 32, so this over this is going to be equal to W over 20. Right? W is the same as 20. Okay, so now I cross multiply, I get 32W is equal to 20 times 75. W is equal to, you're going to do this on your calculator, but it's 20 times 75 divided by 32, which is 46.875. Okay? That's the width of the river right here, E to F. Ratio of areas. If two polygons are similar, the ratio of their areas is equal to the square of the ratio of their corresponding sides. So this is like the first time now in this entire lesson that we've learning something new. Okay, we've just determined, we found out something new here, the ratio of the areas. If the two polygons are similar, so polygons here now we're talking about not just triangles but quadrilaterals as well. The ratio of their areas is equal to the square of the ratio of their corresponding sides. Okay, so let's see what that is, what we're talking about here. Example, if the sides of two similar triangles are in the ratio of 3 to 5, find the ratio of their area. Okay, so similar triangles can be used to measure the heights of objects that are difficult to get to, such as trees, tall buildings, and cliffs. They can even be used to measure distances across galaxies. Okay, so if our ratio of corresponding sides is 3 to 5, 3 over 5, find the ratio of their areas. So the ratio of their areas then would be equal to the big area is equal to the small area times the scale factor, in this case K, squared. Right? And its scale factor here, if the ratio is 3 over 5, our scale factor 5 divided by 3, your big area then would be equal to your small area times 3 over 5 squared. I'm running out of space here. Let's look at it in a problem. Okay. So the shaded area is to be an industrial zone, this area here. Okay. Find the area of the industrial zone. So we want to find this area. Assume that king and queen are parallel here and here, and that all streets and the track are straight. So this is straight and this is straight. So we have two triangles here. First thing we want to do is to see if they are similar triangles. Okay. We know that we share this angle and this angle. And then also by angle theorem, we know these two lines they've told us are parallel. So we know that this angle here by Z pattern is equal to this angle up here. Okay, here's my pattern. You guys see that? Engineer, don't lose me here. This angle is equal to this angle by Z pattern. Okay, so by angle then, we know that our triangles are the same. Triangles are similar. Okay, well once they know they're similar, we know that the ratio of their areas, this area over this area, is equal to the square of the ratio of their corresponding sides. So the area of, let's say, the big triangle over the area of the small triangle is equal to the scale factor k squared. That's what we know. This is the new thing that we've learned. Okay, so the first thing to find out is we want to get k, which is our scale factor. Okay, just another way of saying the ratio of the sides. And again, I like to start with the larger triangle over the smaller triangle. Here we can see 3, and here we can see 1 in these two similar triangles. So we get 3 over 1. So our k or scale factor is 3. Okay. We also know that in this particular case, if we wanted to get area, our big area, or let's do it the way I wrote it out. Okay. I wrote our area of our big triangle over the area of the small triangle is equal to the scale factor squared. Okay, so the area of our big triangle is equal to the area of the small triangle, right? We're going to multiply both sides by AS, so AS would cancel out here, and then we would have AS k squared on the other side, right? So we have this happening. So now we know that the area of the shaded area is going to be equal to the area of the small triangle times k squared. So the only thing we really don't know right now so far is the area of the small triangle. So we need to find out the area of this. Okay, we know that area of a triangle is equal to base times height divided by 2. This is something you just need to know from grade 8, I think. Okay. So the base of this triangle here, we can say is 1, right? We're going to go this way. Here is 1 times the height. Here they tell us, very conveniently, here the height is 1.4. And then we're going to divide by 2, so we get our area of 0.7 squared. Sorry, kilometers squared. We know that's in kilometers because all of these units are in kilometers. We know the unit is squared because the base is in kilometers and the height is in kilometers. So you need to multiply those, so it's 0.7 squared. So therefore, going back to this original equation here, we get this. Area of our big triangle, 6.3 kilometers squared. Take our small triangle, 0.7.